Hello students, good evening, welcome to Wallah and welcome to lecture series of theory of computation. So in our previous classes we studied some topics related to theory of computation. That is the first topic, finite automata topic we discussed. In that especially deterministic finite automata concept we discussed. Deterministic finite automata is a lengthy chapter. There are so many topics involved in that. One of the topic we discussed in previous two classes. So before going to start, I am Venkat Rao. I am taking theory of computation and compiler design subject here in Wallah. Right. So in our previous sessions we discussed about the deterministic finite automata, DFA. So we have seen what is DFA. Deterministic finite automata is given. How to identify language from DFA. This is what the topic we discussed in our previous session. In yesterday's class mainly our topic is this one, right. So today's session also of similar nature. In today's session deterministic finite automata only, mainly the reverse concept of this one. If language is given, construction of deterministic finite automata from the language. If language is given, right. Video audio clear, right? Okay. So today is this topic. In our today's discussion we are focusing on how to construct deterministic finite automata for the given languages. So in yesterday's session these two are the common type of questions we are getting in GATE papers. If language is given, construction of DFA, DFA given, detection of language, recognition of language. So in our previous class we solved so many GATE questions. If DFA is given, how to detect language from the DFA. In that the powerful method, elimination method, by using that elimination method how to solve questions. So that technique we studied in previous class. In today's session we are observing some other technique of DFA, right. I think yesterday class is very clear for everyone. Still if anybody having doubt, please watch recording once again, because in these times so many questions we got DFA to language and DFA to language type of question, detection of language from the DFA questions. We have seen many questions in the GATE paper, right. So yesterday topic is very important. So watch recording if you have any confusion, otherwise you can ask me doubts in the chat session, right. So before going to this topic in today, let me cover one small topic, that is overview of theory of computation, languages automata relation. So from that also we are getting many questions in GATE papers. So let me complete that one first, then I'll go for the DFA construction part. So this is our overview diagram of theory of computation. So we have 4 languages, 4 automata. Theory of computation is all about 4 languages, study of 4 languages, study of 4 automata. What are those? First one is regular language, its automata, finite automata. Second one is context-free languages, its automata, push-down automata. These are languages. Third one is context-sensitive languages, its automata, linear bounded automata. Next one, recursive enumerable languages and the corresponding automata, Turing machine. So theory of computation is a mathematical study of computer science. That means by using this study, we are concluding which problem solvable, which problems not solvable, and so many other applications also there. In that, in this mathematical study, mainly we are focusing on, our focus is mainly on automata languages. Here we are studying about 4 automata, studying about 4 languages. Right. From this, 1 mark questions many times asked in gate paper. There are so many questions of 1 mark. Some questions are very easy directly from this concept, relation between automata and languages. Solving those questions becomes easy once you know the relation clearly. Right. This is a subset superset relation. If you observe this relation, it is clearly a subset superset relation. Total topics of theory of computation looks in this way. The relation between topics of theory of computation, if you observe, looks like this. That's why from this repeatedly we are getting questions. That is easy questions. 1 mark questions we are getting, very easy to solve as well. So that topic will conclude, then we go for DFA construction. So what we can say here, the automata possible for this regular language is, I can say, finite automata. The automata possible, it is there anyhow here. Let me write clearly. The automata used to construct for context free languages is push down automata. Automata used to construct context sensitive languages is linear bounded automata. Automata used to construct recursive enumerable language is Turing machine. Right. Now the relation between the languages is subset superset relation. Regular languages are subset of context free are subset of context sensitive of subset of recursive subset of recursive enumerable. So this is the relation, it is clearly visible, and how this relation comes, that we will see in grammar class. We will study a concept called as grammar. In that I will explain clearly how this relation exists. But anyhow, at this stage, this is a relation. If you see any basic book of theory of computation, this diagram will be there. So from this diagram, many times we got questions in gate paper. So now we have to frame, anyhow, based on the grammar rules, we framed the relation between languages. Now we have to frame relation between our automata. The automata exists for regular language, finite automata. The automata exists for context languages, push down automata. In short form I am writing, it is PDA. The automata exists for context sensitive language, linear bounded automata, Turing machine. Anyhow, these are languages. Languages are set here. That's why subset, based on subset superset relation, we have framed like this. Then how the comparison between automata is done? What is automata actually? Automata is a machine that is used to recognize these languages. So in order to compare the relation between automata, we need to use a term here called as expressive power. See, there is a terminology here, expressive power. It is there, but if you see here only, number of languages accepted by particular automata known as expressive power. Good evening everyone, once again. This is a continuation of our yesterday class. This is a new topic, small topic I have taken so that everybody is joining, so that afterwards I will start our DFA construction in today's session. So expressive power is nothing but number of languages accepted by particular automata. If one automata is accepting 5 languages, Automata 2 is accepting 10 languages. Automata 1 accepting 5 languages. Automata 2 accepting 1 languages. Then expressive power of Automata 2 is more. Like that. Number of languages accepted by Automata is expressive power of that Automata. Which Automata accepts more languages, that is more powerful. Powerful in the sense, in the form of expressive power. Like this, I think this is a clear. This is a number of languages accepted by particular automata. This is the important definition used to compare our automata concept. So if you see finite automata and push down automata, which is powerful? Out of finite automata, push down automata, which is powerful? Power wise, if you see, number of languages accepted by finite automata, regular only. Number of languages accepted by push down automata. See, push down automata accepting context free. Based on this relation, subset superset relation, every regular is also context free. It's a superset. So it is accepting the super language, means sub language also easily it accept. That's why language accepted by push down automata is nothing but regular as well as context free, CFL. Regular as well as CFL. That's why if you see the power, if I want to give the power relation out of finite automata and PDA, PDA is more powerful. Finite automata and push down automata is more powerful. Similarly, number of languages accepted by LBA, if you see, LBA can accept regular, CFL, CSL, because it is superset. If any automata is accepting super language, means sub language it will accept very easily. That's why language accepted by LBA, if you see, regular, context free, context sensitive. So out of LBA and PDA, if you see, LBA is powerful. So Turing machine accepts all languages, whatever is written here. So Turing machine is the most powerful one. So this is our relationship. This is the relationship between these automata and these languages. So this relation already it is there here. In theory of computation, we have 4 automata: finite automata, push down automata, linear bounded automata, Turing automata. We can say Turing automata, Turing machine, both are same. If these many machines are there, definitely the concept of comparison comes. If you see in point of view comparison, the point of comparison out of finite automata and push down automata is more powerful. Out of push down automata and linear bounded automata more powerful, and Turing machine is most powerful one. So out of all these automata, 4 automata, the most powerful automata is Turing machine, least powerful automata is finite automata. Some students can get the doubt like this: sir, why these many automata? You are saying Turing machine is most powerful one. We can use Turing machine directly. We can use, but what is the problem? Complexity. In computer science, we have a beautiful terminology called as complexity. If I want to construct for one simple language, if I want to construct a finite automata, it takes 5 minutes time. For the same language, Turing machine is taking 15 minutes time. Then time is one of the crucial element in our computer science, because finally these things we have to turn into machine. Machine has to take less time. Which program is executing in less time, that is best one, because time is our primary criteria. Memory somewhat we can manage nowadays because of these clouds and all this, but time is a very crucial one. That's why, if not possible finite automata, any language is not possible by finite automata, that is, we'll try with push down automata. Not possible with push down automata. Try with LBA. Not possible with LBA. Try with Turing machine. This is what going in general. Right. Then each of these automata exist in two variations, two versions known as deterministic and non-deterministic version. These every automata exists in two versions, deterministic and non-deterministic things. So whenever you say finite automata, we have deterministic finite automata, non-deterministic finite automata. In our yesterday discussion, it was deterministic automata. In future classes, we will discuss non-deterministic automata. So this is called as deterministic finite automata. The diagram looks very scary, but very easy, this one. Right. Like this, every automata available in two versions, deterministic and non-deterministic finite automata, deterministic finite automata, non-deterministic finite automata. Push down automata, deterministic PDA, non-deterministic PDA. LBA, deterministic LBA, non-deterministic LBA. Turing machine, DTM and NTM. Alright. If it is exist like this, whenever we have two automata nature, we have to compare them with expressive power. So if you see the expressive power of this, always we cannot say, there is no guarantee always same. The expressive power of deterministic finite automata, non-deterministic finite automata is equal. Here it is equal. But the expressive power of push down automata, if you observe, they are not equal. The expressive power is, here it is not equal. Not equal means somewhere it should be more. It is not equal. This is more. Expressive power of DTM and NTM is once again equal. Expressive power of DLBA and LBA is, it's unknown, it's an open question. So this is what the final thing. So most of the times we are got, this is the complete diagram. From this we are getting the question. Language relation, their automata relation, its subcategory automata relation. Language relation is subset superset relation. Automata relation is expressive power relation. So out of finite automata, push down automata, PDA powerful, LBA powerful, out of LBA TM powerful. And in finite automata, deterministic, non-deterministic natures. In that, expressive powers are equal. In PDA case, not equal. Turing machine case, equal. LBA case, open question. So this is what the expressive powers in general. Right. If the expressive powers are same, we have advantage. Whenever expressive powers are same, the advantage is non-deterministic machines will be converted into deterministic machines. If expressive powers are same, non-deterministic machines easily converted into deterministic machines. If expressive powers are not same, that thing not possible. Non-deterministic machines cannot be converted into deterministic machines. right? So that's why, see here, first point, expressive power of NF and DF is same, hence every NFA is converted into DF. Expressive power of finite automata same, that's why every non-deterministic finite automata converted into deterministic finite automata. Second point, expressive power of NPADA is more than DPDA. Non-deterministic push down automata is more than deterministic push down automata, hence conversion is not possible. Whenever powers are not same, not possible. Third one, expressive power of DTM NTM is same. Deterministic Turing machine, non-deterministic Turing machine is same. If same, what happens? Non-deterministic machine can be converted into deterministic machine, conversion possible. Here also non-deterministic machine is converted into deterministic machine, but that situation is not there in the push down automata case. So this is our overview of theory of computation. This anyhow, by end of class we are concluding with proof how this is happening, but as a we are starting the subject initially, so you should know what is the how this language looks like. Just an overview, we are not going in depth. How this automata looks like, you may think why these many automata, what is the difference? The difference is expressive power. Whenever you say automata, difference of this automata will be expressive power. There are some automata having less expressive power, there are some automata which is having more expressive power, right? Now the thing is, how we are getting questions from this in the exam. There are so many questions asked from this chapter in the GATE exam. Let us see how the questions will be. I think it is clear till this part, right? This is very, very important. Mostly in after every 2 or 3 classes, we will study this diagram. Because study of theory of computation is nothing but this one only, the whole overview of theory of computation. So after every chapter, after end of every chapter, we will study this diagram, because so many things are there to conclude from this diagram, right? We got one question in 1 year paper. This is the GATE question. So see this question from the same topic. From this topic, the questions generally will be like this. Let DF and DP are number of languages accepted by DFA, DPDA respectively. Let NF and NP are number of languages accepted by NFA, NPDA respectively. Which of the following is true? Any answers? So just if you want to solve this question, this is the diagram. Same thing. So always keep this diagram in your mind. There are so many questions which are there in previous papers from this diagram. So easily 1 mark question will get the GATE paper. Right. So what is the question here? Number of languages accepted by NFA, DFA, NPDA, DPDA. See this diagram. What is this diagram is saying in PDA case? The subcategory automata. Finite automata case, number of languages same. Push down automata case, number of languages not same. That too NPDA. This NPDA is more. It is accepting more number of languages. That is what we studied. So based on this question is given. So generally, what should be the answer? Finite automata case equal, eliminate from options. Finite automata case equal, push down automata case not equal. But what is happening in the option A? He is saying equal here. See this? Equal here. That's why this is not our answer. Come to the option B. NF is NFA, DF is DFA. Finite automata case, number of language should be equal, but here is saying NFA more. That's why this is also wrong op. Easy one. Come to the option C. Most of the students will try to give option C as the answer, but see this clearly. Finite automata case NF, NFA, DF, DFA, finite automata case equal. But what about push down automata case? Not equal, okay. Which PDA more? Non-deterministic push down automata more. Actually, he has to give like this. Then it will be correct. But he is showing here deterministic push down automata more. So this is also wrong. So the answer for this will be none of this. So this is the concept, very easy one, and most of the times we got questions from this. Right. So this is about this topic, overview of languages and automata, relationship between languages and relationship between automata. Right. Okay. Then we will move into our DFA concept. Now the question is, so we today our topic will be on DFA constructions. We need to construct the deterministic finite automata for the given languages. This is also one of the very important one for 2 marks. DFA to language, whatever we studied yesterday, that is the important thing for 2 marks. 2 mark questions mostly will get from these 2 type of topics. If DFA is given, detection of language is given, construction of the DFA. Now the question is, construct DFA for this language. We have to construct DFA for this language. A power n, B power m, n greater than or equal to 1. Is there anybody? Can you answer how to construct DFA and tell me how many states? Construct DFA, how many states are there in the DFA? While if anybody watching recording, after this, whenever you are watching recording, pause for some time, you construct by your own, give answers. That is best way to practice DFA constructions. So here, to construct DFA for this, the answer is DFA not possible. DFA not possible. DFA not possible for this because just now we have seen push down automata is more powerful than finite automata. Because what is the meaning of that? There are some languages which are not accepted by finite automata. To recognize that, we have push down automata. Push down automata more powerful means what? It is accepting more languages which are not even accepted by finite automata. So there are some languages here. Before going to start construction part, deterministic finite automata construction part, we have to see there are some languages which are not possible for finite automata structure. That means there are some languages for which we cannot construct DFA. The construction of DFA not possible. So before going to start, what generally students will do is, whenever I give question, construct DFA, directly they'll start constructing. That is not the right way. First of all, DFA possible for that language or not possible for that language, you observe. Because for every language DFA not possible, that we have seen with big diagram. There is a limitation for the finite automata. There is a limitation for the push down automata also. That's why that big automata Turing machine is there. That's why whenever you observe any language, the first thing what you have to study is whether DFA possible or not. Right. So we'll study that. by looking at the language. Let me show you some language here. There are some languages. For which of the following language DFA is possible? There are some languages. For some of this DFA possible, for some of this DFA not possible. So we need to understand for which type of language DFA possible, for which type of language DFA not possible, because this is the minimum requirement. Without knowing this, directly if you go and start designing, then problem goes wrong, because there are languages for which DFA not possible. If not possible, if you construct, clearly that is a wrong automata, so we'll get negative marking, right? So now we'll see what is the limitation of finite automata. Where limitation finite automata fails, that means where DFA fails to recognize some language, where DFA fails to construct for some language, what is the reason? Those things we'll study, right? We'll come to this. If you want to answer these questions, you should know about some of the just a minute. Okay. When DFA possible for a given language, when DFA not possible for the given language, if you want to observe, analyze from the given whatever the language is given, from that if any comparison exists or not. In any language of this nature, if comparison exists, DFA not possible. Comparison between symbols exist, DFA not possible. Comparison not exist, DFA can be possible. That is a simple fundamental rule, very easy one. So directly blindly don't construct. Whenever you see the language, don't construct. Comparison exist or not exist, observe first. Comparison exist, DFA not possible. What does it mean? Let us see. See this language, previous one, A power n, B power n language. Let us try to construct some strings from this. Number of A's more. So 3 A's, 2 B's, 5 A's, 1 B, and so on. This way. The language structure is like this. How to check whether comparison exists between the symbols or not? If there is a dependency between symbols, then we'll say comparison exists. While generating the number of symbols of the string, if dependency not there, if they are independently there, then we'll say comparison not exist. Let me see what does it mean. See here number of the language nature is A power n, B power m. A power n, B power m. Number of A's more than number of B's. That means whenever generating the string, A should be more than B's. A should be more than B's. Number of A should be more than B's. Right. So if I take my number of A's as 6, how many B's possible? Can I take 10 B's? Can I take 100 B's? No. So the generation of number of B's clearly depending on the value of A. This is called as dependency. This is called as comparison. We are not generating the symbol B string independently. Whenever that independence is not there, DFA not possible. That means whenever dependency is there to generate the string, to generate the number of B's here, we need to check how many A's are there. So if A's are 6, definitely less than this. That means I can generate 4, 5, 3 like this. So for such type of languages, DFA clearly not possible. That is what the meaning. Comparison exists means this is what. So here if I want to generate one more thing, number of A's are 10. How many B's I can generate? Definitely less than 10 because A's are more here. So can I generate 100 B's? No. So B's generation depending on the value of A. Dependency exists. Gone. Like this. So the language nature is the number of B's generation always depending on number of A's generation, number of A's value. So comparison exists. Comparison exists. Then DFA not possible. Comparison exists, then DFA not possible. This is the fundamental rule. Very simple one, very easy one. So that's why you have to check whether DFA exists or not for a given language. That means comparison exists or not. Comparison exists, dependency exists, DFA not possible. So based on this, we need to solve for which of the languages, which of these languages DFA possible, which of the language DFA not possible. In the DFA construction concept, if DFA possible, then only we can construct. If DFA is not possible, how can we construct? That's why first check whether it is DFA possible or not here. Let us take one by one. We will take selected languages. Let us come to the second one first. Second language. Let us solve second language. A power n, B power n, n greater than or equal to 1. Is it DFA possible for this? The meaning of this language is whenever you say A power n, B power n, I am taking assume 10 A's. How many B's I can generate? Any comparison exist here? Any dependency exist? Yes, the B's generation is clearly depending on A's. Generation of number of B's clearly depending on A's. So if it is 10, what is the meaning of this language? A value, B value should be same. I cannot generate 100 B's. I cannot generate 2 B's. I cannot generate 1 lakh B's. It should be exactly same. So if you want to generate B's, we have to compare with A's. Comparison exists, dependency exists. If it is exists like that, not possible. DFA not possible. Let us check this one for the first one. Language L1. Is it DFA possible or not? Here see, I am writing this one here. It is A power n, B power m. DFA possible for this? So n value can be anything, m value can be anything. N comma m greater than or equal to 1. It can be anything. So if I take A value as 10, what about B? Is there any dependency on B and A? This is n, A value is n, B is m, it can be anything. So I can take 100 B's, I can take 1000 B's, 1002 B's, any number of B's. So while generating number of B's, need not to depend on A's. While generating number of A's, need not to depend on B's. A's and B's are there independently. There is no comparison between symbols. If whenever this independence is there between generation of symbols, comparison dependency is not there, then DFA we can construct. So for the first language, DFA can be constructed. Very simple. Freedom. If you have freedom, possible. Remember like this. If you have freedom, DFA possible. Freedom not there, dependency is there, then DFA not possible. Remember in this way, it's very easy. Right. So in this 1 and 2, DFA possible for the first one. DFA possible for the first one, DFA not possible for the second one. Let us come to the third one. What is your opinion about the third language? A power n, B power m. N and m. N is less than m. A power n, B power n. N is less than m. So here number of A's less than number of B's. So any dependency, if I take 10 A's, can I generate any B's? Is there any freedom on B? No. Definitely A value should be less than this. So it should be more. So can I take 2? No. B value as 2? No. B value as 3? No. Definitely 15 or 20 something we have to take this way. So generation of B, we are getting dependency. Dependency exists, clearly DFA not possible. So DFA not possible for this also. DFA not possible. The reason is clearly explained here. Right. What about the fourth one? A power n, B power n. So A power n, B power m. N is not equal to m. N value and m value is not same. Not same means it can be more, it can be less. Here also we don't have independence, because if I take A value as 10, can I take any number of B? Can we take any number of B? That is not allowed, because it should be not equal. A value not equal to B value. So we should not take 10, some other. That means dependency is going on still. I cannot take any number of B's. So if dependency is there, not possible. DFA is not possible for this also. What about fifth one? Observe the language. A power n, B power m. A power n, B power m, C power n plus m. C power n plus m. What is the meaning of this one? Number of A's and B's should be equal with number of C's. The C value is sum of A's and B's. That means if I take 2 A's, 3 B's, how many C's allowed? Can I take any number of C? Is there independence on C? No, the dependency is there here. The C value should be equal with A's and B's. So dependency is there. Dependency is there. Clearly DFA not possible. Right. Come to the sixth one. L equal to A power n, B 2 power m. N comma m greater than or equal to 1. A value can be anything. B is a symbol here. 2 is another symbol. 2 power m. So any number of A's, any number of 2's. That is what the meaning. So DFA clearly possible. DFA possible. So out of all these languages, this is the situation. So that's why before start construction of your DFA, before you're going to start this DFA construction, directly don't construct, because there are so many situations. There are some languages DFA cannot recognize, because we have some other powerful automata, push down automata. Push down automata is there. What is the reason of push down automata? The strings are the languages which are not accepted by finite automata, it can able to handle. That situation we studied. Then every language is not accepted here by finite automata because there is a limitation of finite automata. What is that limitation? That also we studied. The limitation is nothing but dependency problem. If there is a dependency between symbols, then it is very difficult to construct DFA. Then for such type of language also we have to go for other automata, whether push down automata or Turing machine, right? So that's why all these basics are required to construct DFA. Directly don't start and construct, because there are some languages for which DFA not possible. Where is that? Dependency or comparison exists between symbols. If independency is not there in the symbols generation, strings generation, DFA not possible, right? So this is about DFA possibility and not possibility. So out of here there are 6 languages are given. For first one DFA possible, for last one DFA possible, the remaining 4 languages DFA not possible. With this understanding, if these concepts are clear, then we will go and start construction of DFA. I hope everybody is getting this. If you are having any confusion anywhere, watch recording again. If you have any more doubts, ask me in tomorrow's session in the chat box, right? There are so many other complicated languages for which how to analyze what is the problem of construction of DFA, why it is not possible, why it is possible. All these things we will study clearly in depth in our proper course. This is a small series, theory of computation series. Some of the major concepts we are covering here. So many difficult questions, tricky questions, those things we will cover in the coming sessions. If it is not possible in this, in our app classes in GATE Wallah, I will cover all those tricky questions of previous GATE. Right. So let me start this construction of DFA. Now I am going to give you a language. Construct DFA for the language. A power n, b power m, n comma m greater than or equal to 1. Is it possible or not for this? Just now we analyzed DFA is possible for this. We can construct clearly. We can construct DFA clearly for this. If DFA is possible, how to construct? So now let us start construction. Before going to start constructing, let us generate some of the strings. Try to understand what is the nature of the strings. Let me generate some strings here of this language. The minimum string is AB. 2A's 1B possible, 1A 2B possible, 3A's 1B possible, and so on. Any number of A's followed by any number of B's. The type of strings generated by this language is any number of A's followed by any number of B's. Number of A's can be anything, number of B's can be anything, right? So to construct DFA, we need to analyze that 5 tuple notation. This 5 tuple notation help we want. So if you want to construct DFA, all these 5 things we have to mention, starting from the initial state. So to construct DFA, first we want one initial state. So this is the way. Whenever you are trying by your own, generate one minimum string, generate strings like this, start from the initial state, accept all these strings one by one, accept these strings one by one, and corresponding transitions we have to give in the automata. So starting from the initial state, first I am accepting the string AB. If you want to accept the string AB, how the transitions will be? We need two more states here. To accept AB, for A, it has to go to non-final state. For B, it has to go to final state. This is the way of accepting AB. So I am starting from the initial state. First I am accepting one string AB, because AB is valid string, belongs to this language. So this is the concept which is reversed to the previous topic, yesterday's topic. DFA is given, we identified the language. Now language they are giving, we have to construct the DFA. That too, it is a valid language for which DFA possible. Right. So AB, first accept the minimum length string. Then 2A's 1B it has to accept. Starting from the initial state, for 1A, already transition is there, 2A's 1B. For 1A transition, for one more A, like this, if B comes, already transition exists. For A transition exists, for B transition exists, for the middle A, self loop. So second string also accepted. Accept the third string. A to B's. Start from the initial state, accept the third string, 1A accepted, 1B accepted, for the second B, self loop. Then check for the fourth string. Like this, every string we have to give to the automata. Take the string from the language, give to the automata. To accept that, provide corresponding transitions. That's all. This is the way of construction. So here 3A's, 1A, 2A, 3A, followed by 1B, accepted. This string is accepted. Take some other string of this language, 5A's, 6B's, 5A's, 6B's also accepted. So now everything whatever is present in this language, everything whatever is present in this language will be accepted by this DFA, this automata. Whatever is present in this language, clearly accepted. Whatever is present in this language, clearly accepted by this automata. See my terminologies. What I am saying, whatever the strings present in this language, clearly accepted by this automata. I am not saying it is DFA, because is it DFA? Accepting everything, but is it DFA? No, because after accepting our all strings, the automata need not be a DFA. But what is our concept? We are constructing DFA, Deterministic Finite Automata. So even though accepting everything, but if it is not becomes into a valid DFA, we need to attach one beautiful state here called as dead state. Yesterday some people are asking about this. Now this is our dead state. What is dead state? Even though it is a valid automata but not satisfying definition of our DFA, then add one non-final state by providing self loop to all symbols. Then for the remaining symbols, whatever the missing transitions are there, provide edge to dead state. From Q0 missing transition is B. From Q2 missing transition is A. Now see, so what is DFA? Every state, every symbol transition should exist. If every state, every symbol transition exists, then only it is called as DFA. Now see what happens from Q0, A transition, B transition. From Q1, A transition, B transition. From Q2, A transition, B transition. From that state, anyhow, it is all transitions possible. Now see our phi tuple. Number of states 4. Input symbols 2. Initial state 1. Final state 1. Transitions clearly there. So this is the way of construction. This is our valid DFA, that is accepting all strings. And there is one more beautiful property of deterministic automata. The major difference we will see between deterministic and non-deterministic automata is deterministic automata answers everything. So if you ask about valid strings, it will say accepted by reaching final state. So there is a beautiful concept between deterministic and non-deterministic. Deterministic things are very, very good. That's why most of the questions will get from deterministic things. Deterministic automata answer about everything. Answers about valid things, answers about not valid things. So if you ask any string belongs to this language, any valid string belongs to this language, it will say the string is accepted by reaching the final state. If you ask about any invalid string like this, B followed by A, then also it will give answer, this is invalid by reaching non-final state, B followed by A. So for a valid string it will give answer, for invalid strings also it will give answer. That's why in yesterday class I told you, if DFA is given, elimination is easy, because the automata clearly visible for us, for which strings valid, which strings not valid. But this situation you cannot observe in non-deterministic automata. Non-deterministic automata gives answer about only valid strings. For invalid strings, it won't answer, for because some transitions missing, we cannot say clearly. The clarity is missing in non-determinism, but clarity perfectly there in determinism. That is the main importance difference we'll identify between deterministic and non-deterministic machines. So that's why whenever it is a deterministic automata construction, we have to give clear clarity on the automata. We have to construct clearly. For all valid strings, we have to show path to final. All invalid strings, we have to show path to the non-final. That is compulsory in determinism, deterministic automata. Right. The one more question is, whenever you say deterministic automata, lot of clarity is required. Determinism means lot of things to be clear. Is it just a construction of DFA sufficient, or we need to construct minimal state DFA? That is one more thing. So in DFA, so many, that's why construction of DFA is a bit complex. So many things involved. One thing is, for valid strings, for all valid strings, show path to final. For all invalid string, show path to non-final. Third one is, just construction is not sufficient. Just construction is not sufficient. Minimal state construction, because sometimes the question will be, construct minimal state DFA. So just construction itself complex means, definitely in gate papers they'll ask questions on minimal state DFA. So if you just construct any normal automata, that is not sufficient, even though it is valid DFA. Even the valid DFA, they don't want that. Definitely they want minimal state DFA. So is it minimal one? Whatever we constructed, is it minimal one? Generally, our direct constructions won't provide us minimal state automata. If we construct directly, we don't get any guarantee of minimal state automata. To get a minimal state automata, we need to apply some more concepts, that is called as minimizations. So those things we'll see in the next class, the coming classes. In today's session, we practice the way of construction. This is example one. So many tricky big states, 5 state, 6 state automata we are going to construct. Anyhow, this is the way. Let me explain once again how I constructed. First, from the given language, generate strings. Generate strings. Start construction of DFA from one initial state. Take one initial state, slowly start constructing. How we have to construct? Take one string, accept. In order to accept this, provide transitions and states. Take the second string. To accept this, provide transitions. To accept third string, provide transitions and states. Like this, after accepting every string, any missing transitions are there, give it to dead state. Missing transitions we have to give to dead state. So like this, we can construct a valid DFA. The DFA need not be minimal DFA. In this example, we may get, but for some other example, we may not get. So minimal DFA at a time construction is a complex one. That's why generally what we'll do in order to construct minimal state DFA, first we'll construct one valid DFA. There are minimization algorithms. We'll apply those algorithms on this valid DFA. Then that minimization algorithms will try to reduce the number of states present in the DFA. This is the overall situation. So minimization concepts we'll see in the coming classes. So that's all about today's session, students. In tomorrow's session, we'll continue how to construct more complex DFA, and then remaining concepts like non-deterministic automata, regular expressions, and all this. That's all about this session. Thank you. See you in our next session. Every day sessions will be going live at 8 p.m. Thank you. See you. Srinivas.